We're at a point where we cannot keep going down the same route we have been going for the last 50, 60 years in a conventional agricultural sense. Things have to change, and I mean, not just because of the policy and legislative requirements that are placed on us, but a realization, I suppose, that, we need to reduce our levels of inputs into systems. In terms of where we're currently at, and of course most of you will know this, in a conventional agricultural sense, perennial ryegrass dominates our recommended species list. It accounts for 95% of forage grass seed sales in Ireland each year. And if you look at the recommended list provided by the Department of Agriculture, it's really only varieties of Italian ryegrass, perennial ryegrass and white clover that appear on that. And of course there's very good reason why most of the research and most of the interest has been in ryegrass in agricultural systems over the last number of years. And it's around its ability to produce high levels of carbohydrates, high levels of digestibility that are associated with it, its potential to produce high levels of dry matter yield, and of course it can respond very positively to numerous defoliations. So it makes it look on the whole like a really useful species, and it is. But of course the elephant in the room, as it were, is its requirement for nitrogen. It's a very hungry species and therefore requires feeding with nitrogen very regularly and at high levels. So when the call from the Department of Ag came in 2012, I had been kind of interested in what had been happening in the past. How did people deal with this issue in the past before there was a large amount of readily available, relatively cheap, although getting more expensive, fertilizer available. And just looking at this page from the crop trials book in the Albert College back in 1903, I think tells some of the story. There's 31 species on that list that were being investigated. And as somebody who is interested in plant diversity, I wondered how we had narrowed our focus down quite so much. There's 11 legume species on that, and the remainder are grasses. Of course, it wasn't just happening in the Albert. There was evidence from other places, the works by Elliott and Newman Turner, for example. And if you look at some of Elliott's mixtures in the Clifton Park system of farming, he was doing it long before Smartgrass thought of doing it. He had his different functional groups of plants in there, grasses, legumes and forage herbs included in mixes. At the same time, there was some indication in the ecological literature about the potential of multi-species swards, but it was in largely theoretical ecology that this was happening. We're beginning to see words like transgressive overyielding and diversity effects. And it's not till you read on that you get to know what they mean, but I'll try very simply to summarize it quickly here. So what we're talking about is if you have 3 individual species grown as monocultures, they will have 3 known yields in terms of their dry matter, for example. So you would expect that if you grew them as a mixture of a third of each species in that mixture, that your overall yield would represent a third of the yield of each species when grown in monoculture. But what these papers were shown was that that was the case, yes, but we were also getting an additional yield or a diversity response, a mixture response. So the yield was greater, I suppose, than the sum of the parts. An unexpected yield was creeping in there. But as I say, most of that work was appearing in kind of theoretical ecology journals and hadn't really been mainstreamed. So I was interested in this and seeing how, why does this happen, and, has it a place in high input systems, for example. So in terms of the mechanisms for it, we believe it's largely down to something called niche complementarity and facilitation. So if you've got one species growing in a sward as a monoculture, it really only grows to about the same height. Its root depth is largely the same. It can only extract nutrients from certain levels of the soil profile. It's limited in terms of the ecological niches it can fill. if you start mixing the sward up with different species from different functional groups and different traits, you can then potentially extract nutrients and various other things from different levels of the soil profile. You can see growth at different times of the year. The different species take up different spaces at different times of the year. And of course, we have that going on both above ground and below ground. And something which hasn't been looked at very much is this below ground part of these multi-species swards. So this was one of the key things, but also facilitation, which I suppose the ability of one plant to try and help another plant grow, if you like. And the best example of that would be the legumes and their ability to fix atmospheric nitrogen and make that available to other plants. So with all of that kind of information at the time, when Smartgrass was being written, I suppose my overall aim at that time was to identify whether a multi-species sward grown under reduced N inputs could provide a potentially viable alternative to a high-input ryegrass sward. So I wasn't looking at trying to generate an organic system here, and I certainly wasn't looking to see could we out-yield ryegrass or outperform ryegrass. I didn't expect that we would. But see, could we find an alternative, because there is no other information available in terms of advisory support, etc. There's no other options for people who maybe want to do something a little bit different, who don't want to put on the levels of nitrogen that are required to keep ryegrass in a sward, or who are concerned about other aspects of their farm management. So we'll look at some of the experiments and the findings from the project. That we started off with a plot experiment because we really didn't know what kind of mix to go with. And in doing that, it was based out at Lyons Farm. We had 112 small plots that were established back in 2013, and they were comprised of between 1 to 3 plant functional groups. So, you know, some of them were only grasses, or they had grasses and legumes, or grasses, legumes and herbs. There was a minimum of 1 species in the case of the grasses and a maximum of up to 9. So we weren't looking to create a species-rich grassland here. These were carefully chosen species that were, you know, put in on purpose into seed mixtures. And we grew those then under varying nitrogen input levels, ranging from 0 right up to 135 kgN per hectare per year. We applied it as urea in the front end of the season. All legume-containing swards were front-loaded in terms of their nitrogen application. But we also had a conventional control, as we called it, which was ryegrass grown at 250 kgN. And that got urea in the front end and can later on in the season, and it was throughout the season that those applications of nitrogen were made. P and K were kept non-limiting based on soil results. And those plots were harvested 8 times a year. So it's not the same as harvest, as grazing, I know, but it gave us some indication of how they could potentially compare with a high-input ryegrass sward. And we took samples for dry matter determination, for nutrient analysis, and also we took additional samples for sorting into the component species. So I was interested to see how individual species established, persisted, and their contribution to dry matter over time. So from each plot, 3 samples would have been taken each summer, or each growing season rather, and each of those samples, every blade of grass, every leaf of clover, every leaf of everything else that was in there, got sorted into different containers and the dry matter determined. So in terms of the results from that work, there's a lot of information summarized in this graph, but on the x-axis, or the horizontal axis, we're seeing nitrogen input. So it's looking from 0 to 135 kgN. On the y-axis, we're seeing kilograms of dry matter that were produced. And I suppose the next most important thing to say is the dotted black line represents the yield over the 3 seasons that we're measuring here from the perennial ryegrass at 250 kgN. As I said, there's a lot of information summarised in it, but the legend on the right gives a breakdown of what the different coloured lines mean. And you can see that there's different numbers, and they're in the order of the proportion of grass, legume or herb that was included in the original seed mixture. So in some instances, and I should have said that our species included in this, our maximally diverse sward, would have consisted of ryegrass, timothy, cocksfoot, red clover, white clover and bird's foot trefoil, and then chicory, plantain and yarrow was in there as well. So it didn't matter it doesn't matter, for example, with these, whether for example, 55% grass was all ryegrass, or if it was ryegrass and timothy, it's all summarised within the line, the blue line, if you like. So what we can see, which is really interesting, I think, is that a number of our mixtures compared really favourably at 0N compared to the ryegrass at 250 kgN. And why is that? Well, it's because of the legume component of them, obviously. They won't do it on their own. They need the legumes in there. And at about 90 kgN input, some of them were actually out-yielding the high-input ryegrass. If we look at that on a seasonal basis, this is spring herbage production. Again, you can see we were kind of surprised that our legume-containing swards yield so well in the spring, that they weren't a bit slower, but a lot of them are comparing very favourably again with the ryegrass. When we look at summer herbage production, obviously ryegrass comes into its own there, and it's out-yielding most of the other mixtures. The only exception is the one that had 60% legume in it, and that's probably not one that most people will be adopting. But, there are questions, I suppose, about how much grass you need and when you need it, that this might help to start addressing for people. And then in autumn, where we got some really nice results, was around the potential of multi-species, I suppose, to yield in the autumn. And quite a number of those mixtures out-yielded the ryegrass into the autumn period. Obviously, they don't stay the same over time, and we look at the compositions a little bit and how they changed. But just quickly on the yield stability, and this would have been taken from the sorting data. So this is 2014, just overall yield from the different sward types. And if you look at where we are with that ryegrass line, the dotted black line, we're about 11 tonnes there. In 2015, it was about the same, but in 2016, we got a very significant drop in the yield from our ryegrass swards, which indicates to me that under the conditions we had at that site, and I should say that the site had been in continuous tillage prior to the establishment of this experiment, so it's probably quite a hungry site, that even 250 kg of applied N wasn't enough to keep the stability of yield up from the perennial ryegrass. But interestingly, a number of the mixtures showed much greater stability. We didn't see that decrease in terms of the mixtures that were there. In terms of the botanical composition, and I just pulled out a couple of these to look at quickly. This purple line at the top represents a mixture that would have contained or would have been sown at 60% legume. So when we look at how that broke down in terms of individual species or individual functional groups contributing to dry matter, we saw that at 0N, about 28% of our dry matter was coming from the grass component and about 70% from our legume component. But when we increase that fertilizer input into the swards, we're shifting that balance. So we're favouring the grass component over the legume component, but we weren't seeing any yield response as the line is very flat. So we're not seeing an increase in dry matter production in response to that. Again, when we look at this one here, which was 55% grass, 35% legume, 10% herb when sown. Similarly, we see, that at very low input levels or 0 N, we get a favouring of our legumes, as you'd expect. And when we increase our inputs into it, our nitrogen input in particular, we end up favouring the grass component over the legumes. Now, there was a yield response there, and I guess that's where people have to make decisions around how much dry matter they need on particular farms and at particular times of the year, and that will help them judge potentially. But it's just to be aware that that's the type of change that we see. Some of my colleagues worked on the estimated nitrous oxide emissions based on the dry matter yields that were being produced from these swards. So just to be clear, they weren't going out and measuring nitrous oxide emissions. They were modelling estimates based on the dry matter that had been produced, the quantity and the type of fertiliser that had been applied. So Paul Murphy did this work. And over 5 different sward types. So there was a ryegrass at 90, which is this first one here, a ryegrass at 250 kgN, ryegrass and white clover at 90, a simple mix, which was a 6-species mix, and then a more complex mix, a 9-species mix, both at 90 kilograms of nitrogen input there. And we can see almost a 90% estimated decrease in the potential nitrous oxide emissions on those swards that had the high legume content within them, or the legume content within them, and had been managed at lower nitrogen input levels, and also obviously with the urea on front. I suppose if we're doing it again, we'd be looking towards maybe protected urea rather than just urea. We weren't just interested in the yields, etc. We also wanted to see what other impacts these swards would have on things like the overall diversity from the different plot types. And we could only look at components of this. So we did look at components of above and below ground diversity. The earthworms are ones that I'll focus on here today. And of course, we didn't want to get in with spades and start digging up our plots. So this contraption here is called an electrical octet, which basically consists of 8 probes, which you push down somewhere about 3/4 of a metre into the soil, and the soil has to be quite damp, and you run an electric current from a battery through that. That's going to irritate the worms come up, and then we can count them and weigh them and collect them, etc. So it allows us to look at what's going on in terms of worms without being destructive to our plots. And they were sampled over 3 years. I've just included 2 years' data here, the last 2 years. The graphs, I guess, for this are a little unusual. When you see them, a kind of a straight line response like that means that there would have been no response in terms of earthworms to the different sward types that we're measuring. Whereas a curvy response, or a curvy plane, as you see in the far triangle, means that there is a significant response to the diversity of the swards. So what we were seeing in these was certainly a significant increase in earthworm biomass in those swards that contained at least 30% of their dry matter was coming from legume. And there was also a significant impact of herb inclusion in there as well. The biomass overall was estimated to be in the region of 80 grams per metre square. So if we convert that into hectares, it works out at about 800 kilograms per hectare, which isn't bad given the history of this site. We think about this site that it had been under continuous arable cultivation for a very long time. So that's overall biomass. When we look at abundance, again, we see a similar story, and my colleague Olaf Schmidt, who's an earthworm scientist, would say that it's certainly the legume component that is driving the earthworm communities here. So the abundance showed similar trends, and we estimated that we'd have about 1.1 million earthworms, adult earthworms per hectare. So there's an awful lot going on underneath the soil. Earthworm species richness. Same story was happening here, although not as pronounced, but it was still happening. We're seeing an increase in the richness across the 3 functional groups of earthworms. So those are the epigeics, which are the earthworms which are living, there's shallow surface dwellers that are working on the very beginnings of the conversion to organic matter. The endogeics, which burrow horizontally in the soil, and then the anesics, which are the big deep burrowers, which bring organic matter down through the soil and mix it. And we're seeing that species richness increasing across those functional groups. So in 2014, 2015, we decided, and Tommy Boland and Bridget Lynch and Connie Grace and all sorts of people were involved in this work and drove this work. We decided it had to move away from small plot work to a larger scale experiment. So we selected 4 sward types. What we estimated were kind of our best performing ones, and established a farmlet experiment on Lyons Hill, on the back of Lyons Hill. So we had a ryegrass receiving 163 kgN, ryegrass and white clover receiving 90, a 6-species mix which was made up of 2 grasses, 2 legumes, 2 herbs. So that would have been perennial ryegrass, timothy, red clover, white clover, chicory and plantain in that one. And then the 9-species mix would have been similar, but would have had the addition of cocksfoot, bird's foot trefoil and yarrow within it. Unfortunately, at the site, we didn't get establishment, or not good establishment, of bird's foot trefoil or yarrow there. But this is the site in question. It was a challenging site. It's on, I don't know how many are familiar with Lyons and the back of Lyons Hill, but there's very thin soils up there. There's rocky outcrops in places. So we felt if it could work here, it could probably work anywhere. So 30 twin suckling ewes were applied per treatment, and they were stocked at a stocking rate of 12.5 ewes per hectare. And the work that was done was repeated over 2015 and 2016. They rotationally grazed 5 paddocks on the hill, and unfortunately in 2015, if you remember, it was a very cold, very slow year. There were concentrates required in 2015. There wasn't in 2016, but concentrates were required across all treatments. So it wasn't just confined to any of the multi-species sward types, it was across all treatments. The kind of measurements that they took, they measured ewe weight and body condition score. Lambs were weighed fortnightly. They were drafted for slaughter at 45 kg live weight, and fecal egg counts were undertaken fortnightly as well. So some of the work, the results that they have found from this work, the impact of the sward types on lamb weaning weights. So this red line here shows our perennial ryegrass monoculture and what the weaning weights were here. The blue one is perennial ryegrass and white clover. Then we have our 6-species mix and our 9-species mix. And we can see from that all of the other treatments were different to the ryegrass monoculture. And if we look towards our 6-species mix, we saw about a 2.5 kg increase in weaning weights on lambs that were out on that sward. The ewes were fed on that sward. If we look at the sward type and the number of days required to reach the 10, ryegrass and white clover, 6 species and a 9-species mix. And what we're seeing there is that for any of the animals that were on swards other than our ryegrass monoculture, we were seeing an approximate 2-week decrease in the number of days that it took them to reach the 45 kg weight. And I suppose if you think about that, it mightn't seem huge, but that's 2 weeks less handling, it's 2 weeks less methane emissions, etc. So if we move on, one of the most exciting results, I think, was generated from the fecal egg counts, where these were measured. And then, of course, the use of antihelmintics was based on the fecal egg counts that have been recorded from the animals. And what we're seeing here is that the number of antihelmintics that were required, or worm doses that were required, were reduced once our diversity in our sward increased. Okay, so we saw it across the ryegrass and white clover, but also the 2 other mixed swards as well. That's hugely important given resistance challenges that are building up and helping us potentially to prolong our use of existing antihelminthics and maybe find alternatives as well. So the question then arises, where are lambs performing so well to the detriment of the ewes, and this is where the body condition scoring came into play here. So you see again in the red is our ryegrass and the body condition scores at 3, I suppose, key points. So at 6 weeks, at weaning and at mating stage. And we're seeing that at 6 weeks and at weaning stage, the ewes on the ryegrass were quite a bit lower than target body condition scores would be there, whereas all of our ewes on the multi-species met the targets and were above those as well on some of our mixes. So I suppose the important point from that is to show that the benefits to the lambs was not coming at the detriment of the ewe. So where are we now? Well, this work kind of coincided, and the results of it coincided with, I suppose, new land becoming available at Lyons. So we got 50 acres were purchased just adjacent to the existing farm, and our head of school was forward thinking enough to think, okay, we want to do something different with this. One of the big challenges for us in research is that the research funding mechanisms tend to be quite short. So you get funding for 4 years. That means you have 3 years to collect data, and you have 6 months at either end to plan and write up. That's usually what it means. And then the funding stops and something else potentially goes into that field that you are working on. So we don't tend to build up long-term pictures of what's happening. We get those few years data. But for this kind of work, I think we really need to see what the long-term picture is. So Alex has said that this land is going under a long-term grazing platform, and this summer we've established an experiment on it, which consists of 3 sward types: a relatively high input ryegrass sward, again, a ryegrass and white clover, and then one of our best performing, or what we think was one of our best performing multi-species mixes. We're basing it on a 6-species mix there. So ryegrass and timothy, red and white clover, and chicory and plantain have gone in there. We have to randomise it and replicate it so that we can publish all this work and that the data from it will be reliable. But we have calves on it at the moment. We're going to be running a calf to beef system on it. What we're looking to do here, if it's possible, is to generate a low input, high output system, or certainly a lower input, high output system. We're stocking those, or we will be stocking them when the animal experiments start next year at a stocking rate of 2 to 2.5 livestock units per hectare. And we're also retaining areas under different land uses. So there are small areas retained on this site. And again, it was a site that was under continuous tillage for quite a long time. We're retaining some areas under tillage, and we've also added in some woodland areas on this site. The reason for that is because we want to be able to look at carbon sequestration over time under different land uses. Now, soil carbon sequestration is going to be a long-term thing, so to answer that question and how much carbon is sequestered under our different sward types and under our different land use types is going to take us quite a long time, hence the need to have a long-term experiment here, which isn't just dependent on funding calls that come about. But in addition to that, we have divided up this site into 2 hectare paddocks. They'll be grazed at 1 hectare scale, but at 2 hectare scale we've hydrologically isolated these paddocks. So each sward type established on 2 hectare paddocks has been hydrologically isolated, and what that means is that drains have been put in around 2 sides of it. The site is on quite a slope. The slope all runs on this site from the top end here, this lower end, right down to the point at the front there. So we are able to put in, or what we hope we're doing it correctly, we've put in these French drains around 2 sides of each of the paddocks, and that will allow us to monitor water quality as well as other aspects of the farm management there. Thankfully, we have received funding for a new project on this called Smart Sward. I get it hard to change away from names. This is funded under the Department of Agriculture again. And so the first step of that long-term grassland work or grazing experiment work is being funded under the Department of Agriculture. We will have to seek continuous funding to keep it going, but the land base is there and there is a commitment to keep these sward types and the infrastructure in place in the long term. At the moment, we've been accepted into the Global Farm Platform, which is a network of sites globally, which I suppose their key emphasis is on increasing the sustainability of ruminant production systems. So we are a member of that platform at this stage. And I guess where we want to get to with this is to be able to answer some or all of those questions that are posing big challenges for us within ruminant production systems. We want to be able to talk about soil fertility, biodiversity, greenhouse gas emissions, pasture resilience, but I think it's not sufficient to be able to do that over a 2 or 3 year time period. We want to be able to do it over a much longer term as well. Okay? Good.